Hi, this is Math 2520, and in this video we're going to be looking at trigonometry substitutions when it comes to integration. And we use this a lot when you see a square root in the denominator, and inside the square root you have an x squared a lot of times. And it can be different forms. It could be x squared plus something. It could be 3 minus x squared. And sometimes there's nothing on the numerator, sometimes there's an x in the numerator. To solve problems like these, we are going to use three main trig identities. First one is a squared minus x squared when x is equal to a sine theta. Then we get 1 minus a sine squared theta, which is cosine squared theta. Right, so if we plug this in, just to kind of show why it works, a squared, you plug in a sine theta, you get a squared sine squared theta. And then you can factor out an a squared. You have 1 minus sine squared theta, and you can take the square root of a squared, and you get a square root 1 minus sine squared theta. We know what that is, so that is a square root of cosine squared theta, which is a cosine theta. Right. So that's why we're going to use these, because of how they work. Okay, so that's the first one. Then I'll just write the other two. Square root of a squared plus x squared. Here x equals a tangent theta. So then you get 1 plus tangent squared theta, which will be equal to secant squared theta. And then the third one, x squared plus x squared minus a squared is going to be when x is equal to a secant theta. Squeeze that little c in there, and that will make that inside secant squared theta minus 1, which is going to be equal to tangent squared theta, which you can then take the square root. Right, so let's go through a problem here. We're going to use a substitution to evaluate 1 over 4 minus x squared to the 3/2 dx. Here we're going to let x equal 2 sine theta. Now, the reason why is it follows this form of square root of a squared minus x squared, where a will be 4, or I'm sorry, a squared is 4, so a is 2, and then we always let x equal a sine theta. And so we can then take the derivative of this, so dx equals 2 cosine theta d theta. And then we can plug in what we have for our integral now. So the top, you have just a dx, so you have 2 cosine theta d theta. And then the bottom, we're letting x equal 2 sine theta, so we have 4 minus 2 sine theta squared, so 4 sine squared theta. And then this is cubed as well, since it's still 3/2. There's still square root there, which it still works same way. Alright, so we can simplify the inside of that radical, and you'll get a 2 on the outside of the square root. When you factor out the 4, you have 1 minus sine squared. And then again, that is all to the third power, including anything that comes out. All right, we can take 2 to the third power, you get 8. And we'll have square root of cosine squared theta, and that is still a to the third power. Now we can take the square root of cosine theta and then raise it to the third power, and we'll have the square root taken care of at that point. So square root of cosine squared is cosine squared, so you have a cosine to the third power. Alright, so now we can simplify. So 4 on the bottom, cosine squared on the bottom. So the 2 cancels, cosine cancels. You have just the d theta. And we can write this now as 1 over 4 integral of secant squared theta d theta. And the integral of secant squared is tangent. So you have 1/4 tangent theta plus c. A lot of steps, but if you follow it all, it will help solve these. Alright, so for these again, I'm going to go through why we use them. So square root of a squared plus x squared, we use that as x equals a tangent theta. And it's because it will lead to secant squared theta. And if you think about it, this is going to be your x, this is your a, and this is your a squared plus x squared. So it's just a Pythagorean theorem. Your leg squared plus your other leg squared equals your hypotenuse squared and if you do that square root, you get again a squared plus x squared. So that's why that one works. For the next one, we use x equals a sine theta, and we'll end up with a cosine squared from it. And this works because here x is your y, a is your hypotenuse, and the other leg is a squared minus x squared. So if we do x squared first leg plus square root of a squared minus x squared squared, that's your second leg, equals a squared. This side will work out to a squared. So we take the square root. You have a squared minus x squared equals a squared, and then a squared equals a squared. And then the third one, x equals a secant theta. Here we will have x be the hypotenuse, a be the vertical, square root of x squared minus a squared. And so we do a squared plus square root of x squared minus a squared squared equals x squared. This undoes that square root, so you have a squared plus x squared minus a squared equals x squared, and your a squares cancel. Okay, so that's why those those work and why we use them. Right, so steps for solving these: look for easy substitutions or an inverse trig function you recognize. Substitute for x, picking either case 1, 2, or 3 above. It has to kind of match that form though. And again, the forms it uses is when you got square roots of a squared plus x squared, or a squared minus x squared, or x squared minus a squared, or anything like that form. And then we go and rewrite the integral in terms of theta and solve for the integral and solve the integral. All right, so we'll look at integral of 1 over x squared, square root of x squared plus 4 dx. And we're going to look at this from integrating from 1 to 2. Okay, so x we're going to use as 2 tangent theta. That's because it's x squared plus 4, that kind of form. And so dx is going to be 2 secant squared theta d theta. One thing we need to do, we're going to want to solve this for tangent, so we'll want to write this as tangent theta equals x over 2. So I'm dividing the 2 over. It's going to help us out. And so we can rewrite some of the integral. On the top you have 2 secant squared theta d theta. That's just because you're dx. On the bottom you're letting x be 2 tangent theta, so you have and x being squared beside, you have 4 tangent squared theta. Then inside here you have 4 tangent squared theta plus 4. Right, so we can reduce some. I'm going to pull it out too. We'll have a 1/2 out front. The 2 and the 4 become 1/2. And so we'll have secant squared on the top d theta, and then tangent squared theta square root, and I can pull the 4 out of there, so we have tangent squared plus 1. Alright. So now it's going to be 1/2 integral. I'm not writing my limits, but they're still there. We gotta remember that at the very end. Take the square root of 4. And you get 2 on the outside. And you have square root, and then tangent squared plus 1 is your secant squared. So we'll now have 1/4 on the outside when we bring that 2 all the way out. Secant squared d theta over tangent squared theta, and then square root of secant squared is just secant theta. Okay, 1 secant will cancel. So secant theta d theta. I missed the theta a couple times. Over tangent squared theta. Now this one probably be easiest to solve by bringing it back to sine and cosine. So tangent is sine over cosine. So that puts sine theta, square theta on the bottom, cosine square theta on the top. And then secant is 1 over cosine. So that puts cosine on the bottom. And then you have your d theta. And then we can cancel here. You have 1 cosine cancel, sine square theta d theta. Alright, so now we got it down to that. To solve this, we'll use a u substitution. We'll let u equal sine theta, du will equal cosine theta d theta. Okay, so now we go through a u substitution. So 1/4. Top will be du. Bottom will be u squared. Okay, we can do this integral. So we get 1/4. No, I'm going to do this first before I do anything. It'll be easier for me to see it. Right, we raise it by 1. So -2 goes to -1. So u to the -1, and then you divide by that -1. And so we can write this as 1/4, where the u is in the bottom, and the whole thing's negative. And we're evaluating from our limits a to b. I know I have limits, I'll put them in at the end. Now we have to go backwards through all this. So -1/4, and then u equals sine theta. Again, we're evaluating this from a to b. And then theta, we have to figure that out based on a relationship. So let me draw this triangle real quick. So for a triangle, we have 2, an x and a y, and then this is 4 plus x squared. Okay, so that's just like that top triangle. We want to know sine theta is going to be opposite, and theta is this one, over your hypotenuse. Okay, so x over square root of 4 plus x squared. Okay, so we'll flip that because sine's in the denominator, 4 plus x squared. Then the 4th on the bottom, and then x on the bottom. And this is what we evaluate from 1 to 2. So we couldn't do our limits until we got it back to x's, because the x's is where it goes from 1 to 2. Yes, you could change your limits if you wanted to, but that would be even tougher. Right, so we evaluate at 2. Negative square root of 8 over 8. And then for 1, do it minus a negative, so it'll be plus square root of 5 over 4. And then we'll get a common denominator. So negative square root of 8 plus 2 square root of 5 over 8. Alright, there's a lot to one of these problems. It's another tool to use in integration, but sometimes you don't just use one tool for a job. This next one, we have 1 over the square root of 3 minus x squared. Here we'll let x be equal to square root of 3 sine theta. So dx is equal to square root of 3 cosine theta d theta. And so we can make our integral then look like square root of 3 cosine theta d theta on the top. On the bottom, we'll have square root of 3 minus square root of 3 sine theta squared. Of course, we'll have to do some simplifying in order to get things to cancel. Oh man. Go back to that. Okay, I'm just going to write what I had. I'm not going to write everything again. I can always go back in the video. Okay, so that's what I had. All right, so we'll simplify this. We'll start with the inside by squaring that. I'm going to bring the square root of 3 out front. Keep forgetting my theta with the top. Theta d theta. Square root of 3 minus 3 sine squared theta. So square root of 3 out front. Cosine theta d theta on the top. Here I can factor out 3. Okay. Now I don't need the 3 to be a perfect square. I can still break this apart. So I end up with a square root of 3 out front. And then on the bottom I end up with another square root of 3 out front. Right, the top is still cosine theta d theta. The bottom here, it's going to be square root of 1 minus sine squared theta. Right. The two square root of 3's cancel out. I don't know why I switched colors. So you have integral cosine theta d theta. And then the 1 minus sine squared theta is cosine squared theta. So this starts to become a lot easier. So that'd be just cosine theta. And so you end up with d theta, one of the easiest integrals we have. You get theta. We didn't have limits. We're going to have to bring this all the way back to what theta equals. We started with x equaling square root of 3 sine theta. I had it written before. All right, we can solve this for theta. So sine theta equals x over square root of 3. Theta equals inverse sine of x over square root of 3. So we can write theta then as this is equal to inverse sine of x over square root of 3 plus c. All right, a couple more problems. Right, so square root of 9 minus x squared dx. We'll let x equal 3 sine theta. Dx equals 3 cosine theta d theta. and we will make our substitutions. So we'll have 9 minus, and x is 3 sine squared, so we'll have 9 sine squared theta. And then dx is just 3 cosine d theta, so we'll have that on the outside. 3 cosine theta d theta. A little bit different than what we've done because we're not dealing with the denominator here. I don't know if that's going to be easier or harder. So we have 9 times 1 minus sine squared theta, and 3 cosine theta d theta. I am going to pull the 3 to the outside, and then we have square root of, well, I'll do it in a few steps. So here I'm going to pull cosine theta first. Square root of 9 will give you 3, so you have another 3 coming out, and then square root of 1 minus sine squared theta d theta. That 3 can come out in front, you get 9 cosine theta, square root of cosine square theta d theta. Take the square root, get 9 cosine theta d theta. And so those can be squared. Now we gotta do the integral. And for this, we can look up the integral we've done for it before. It ends up being, well, let me see if I have. This ends up, there's a trig identity for cosine squared theta. It's a double angle trig identity. So we're going to use that. You can look up the trig identity. So we're not doing an integral for it, but we're going to have 1/2 1 plus cosine 2 theta and then d theta. So that's cosine squared is equal to this as a trig identity. And then we can break this apart. I have integral of 9/2 d theta, integral of 9/2 cosine 2 theta d theta. Okay, first one, not too bad, 9/2 theta. Second one, we can do this, it's not too bad either. Because of the 2 in the inside, we'll get 4 on the outside denominator, because we gotta divide by 2 a second time, and then you get sine of 2 theta. And then again, we can look at our triangle. It's going to be a minus x squared. This is x, this is 3. And so if you want to know sine of theta, it's going to be opposite over adjacent, so x over 3. So inverse sine of x over 3 is equal to theta. And so that gives us, instead of 9/2 theta, we have 9/2 inverse sine of x over 3. then we gotta do the next part. Do it like this. So 9/4 sine of 2 times inverse sine of x over 3. Let me double check how I want to do this. We'll leave it at that. Now if we have an x, we can plug it in, solve out for the numbers. Oh, plus c. Alright, last one. 1 over square root of x squared plus 2x minus 3 dx. And we'll only evaluate this for numbers from 1 to infinity, so negative won't be included here. It's good to know when we're dealing with square root. So here, we're going to make a couple adjustments that may not make a whole lot of sense at the beginning, but there's a reason why we do this. So we'll make this x squared plus 2x plus 1. I'm basically completing the square, minus 3 and then minus 1, so I don't change anything inside there. Dx. And then what I can do is rewrite that in a different kind of form. This is going to be x plus 1 squared. That's why I completed the square. That encompasses these, and that's going to be negative 4. Okay. And then dx. That actually gets us into where we wanted to go with this. So what I'm going to do is kind of a u substitution. I'm going to do u equals x plus 1, du equals dx. So we have du, and then in the bottom we'll have u squared minus 4. That's because we haven't dealt yet with x plus 1 being squared instead of x being squared. We still will use the trig though, the trig value for this, but instead of x equaling it, we're going to let u equal 2 secant theta, du equals 2 secant theta tangent theta d theta. So now this becomes integral of 2 secant theta tangent theta d theta over square root of 4 secant, not sine, secant squared theta, that's your u squared, minus 4. So I'm bringing 2 on the outside. Secant theta tangent theta d theta over square root of 4 secant squared minus 1. Right, square root of 4 would be 2. So we get another 2 on the outside. They will cancel here. Then the numerator, and then your bottom is square root of secant squared theta minus 1. And that is just your tangent squared theta. So 2's cancel. Secant theta tangent theta d theta over tangent theta. You can see things cancel here. So you have secant theta d theta. And secant theta d theta, we had this before, an integral of it, and you get the natural log of secant theta plus tangent plus tangent theta plus c. Alright, so now we have to look at what theta equals. And so again, we'll look at a triangle for this. U squared minus 4, 2, and u. So we'll do 2 of these. So we want to know what secant theta is. So secant is hypotenuse over adjacent, so that'd be u over 2. Tangent theta is opposite of adjacent, so square root of u squared minus 4 over 2 plus c. And then we gotta bring this back to x's. That's actually easier one. We just plug in our x plus 1 wherever we have a u. Hopefully I don't lose this. Right. So I have natural log x plus 1 over 2 plus square root of x plus 1 squared minus 4 over 2. Now we have everything back in x's. Alright. In the next video, we'll look at partial fractions, which is another way to solve trigs. I'm sorry, integrals. I'll see you then. Bye.